Morning everybody. I will present you the general approach, how to define a physical-chemical basis that can be used to predict yam food quality. So, the general approach for developing this biophysical test is first to begin with the processor and consumer demand, and then to develop, for example, sensory evaluation to predict this consumer quality demand that has been presented by Christophe just before. Developed also texture analysis procedures as presented by Lyell, and then after to develop biophysical tests that can predict either sensory evaluation result or textural instrumental measures, or directly to predict quality demand by consumer and processor. It is, for example, the case for the color. You can develop chemical tests for analyzing color. And finally, with this biophysical test, you can develop a database that can be used for NIRS calibration and rapid analysis prediction of the quality of yam by NIR analysis prediction. So I will illustrate this general approach during this presentation, and to see how identify a biophysical candidate for establishing prediction of the quality, define a procedure for this biophysical candidate and write the standard operating procedure, test the reliability of the procedure and its power of discrimination between cultivars, and establish a relationship between the results of these procedures, biophysical procedures, with the quality attributes obtained by textural analysis, sensorial analysis, or consumer demand, and to build a database with this procedure for establishing a NIRS calibration. And so I will give two examples to illustrate this approach. These two examples are water content and pectin content, and I will give you some examples of how to establish the standard operating procedure for determining water content and pectin content, how to see which are the critical points of these procedures to obtain reliable biophysical analysis, and how to establish a link between these biophysical traits and quality, and in this case the quality will be texture analysis. So in any case, the first step is to choose biophysical candidates based on the characteristics looked for by consumer or processors, and this has been performed, for example, in the case of boiled yam in FSA in Benin. You can see the characteristic looked for by consumer and processors, and on the right side of this table, you can see the candidates of analytical procedures that can be used to predict the characteristics looked for by consumer and processor. For example, for color, you can directly measure the color, or try to analyze total phenol to predict the color from the total phenol. In the case of texture, you can directly measure texture by instrumental pentrometry, for example, or TPA, or also you can try to measure starch content, amylose content, and pectin content, for example, to see if there is a relationship between these candidates and the texture in hand or in mouse, measured by sensorial or by textural analysis. And also it can be water content, for example, fiber content, cell wall content. In the case of taste, of course, you can measure the sugar levels that can be linked, we suppose, with a sweet taste. So if you suppose, for example, that water content is an important biophysical trait that can predict the texture of your product, you have to define the procedure to evaluate water content. This has been, for example, performed during the RTB food projects, and an SOP has been written by IITA in Nigeria, and this procedure is very simple. You have to dry your sample over 100 degrees C for a minimum of time of 24 hours. In fact, you weight your sample before and after drying until constant weight, and the difference is the water content. It is very simple, but even with this very simple procedure, you have critical points, and the first one is the way you fragment your sample before drying. You can use chopping, grating, blending, but in any case, you have to fragment very finely your product before drying, otherwise the result will not be okay. So we identified mainly 3 main critical points on this procedure. The way wet samples must be duly finely sliced, homogenized, or blended before drying. The second critical step is that the cans, where you put your samples, should be completely cold, not warm, before weighing. Otherwise, the weight is not true. And lastly, you have to perform at least 2 or 3 replications to obtain correct mean value of the water content of your yam, and I will illustrate this in the following. So, concerning the reliability of water content, we will see that it is problematic, and it is the same for all the components in the case of yam. So, if you look at the tubers, you can separate 3 portions, for example, in the tuber, and slice the tuber and examine and determine the water content in this portion, proximal, central, and distal. And you can see that there is a large variation of water content between the proximal, central, and distal part of the tubers. For example, for the proximal part, you have a water content for 1 cultivar BTBT, which is between 35 and 45%. For the same cultivar BTBT in the distal part, the water content is between 27 and 31%. You can see this large variation. In addition, there is a large variation between tubers. Here you have 3 tubers, the blue one, the red one, and the green one. And you can see, for example, for the proximal part, that they are this large variation due to the variation between tubers. So there is a large heterogeneity of water content within tubers and between tubers. So if you want to determine water content in yam tubers, you have to perform the analysis on several tubers, and in addition, you have to perform the analysis on several samples in each tuber to obtain a correct value of water content. So as soon as you have established the water content of tubers, you can try to establish a relationship between this water content and the quality of the tubers. And this has been performed, for example, in the case of pounded yam 10 years ago in a study performed by FSA in Benin. They first established the QDA by sensorial analysis of the pounded yam, and they have been shown that 2 types mainly of attributes are very important, which are on the left side of this PCA, the texture of the pounded yam. This is smoothness and elasticity, and on the right side of the PCA, the bitterness. And if you look mainly at the elasticity, they also establish the relationship between the QDA score, elasticity, and the hedonic score. And for hedonic score over 0, which is a hedonic score which is appreciated by consumers, you should have a QDA score for elasticity over 10. And if you do the relationship want to establish the relationship between this firmness and the biophysical analysis of tubers, you can see that there is a quite good correlation between elasticity and dry matter content. Okay, and for elasticity over 10, which is elasticity looked for by consumers, you should have, in this case, a dry matter content which is over 35%. Also, in this study, you can see that there was no correlation between the sensory elasticity and the firmness measured by extrusion with a Stevens texturometer. So in this case, this, for example, texture analysis was not appropriate. But this correlation between dry matter content and elasticity is not perfect, and you can see that there is some samples which with a quite high dry matter content, but which does not give a proper good elasticity. Okay, so other constituent, other component can also have an influence on elasticity. So in a second publication, they also establish another correlation between firmness of bonded yam and dry matter content, but also by addition of starch content and amylose content. You can see that this correlation in this case is better, and you have a very good prediction of firmness by taking into account the dry matter content, the starch content, and amylose content. After that, when you have established that water content is an interesting candidate for prediction the texture of the yam, for example, for pounded yam, you have to establish calibration, and this has been established, for example, in the case of yam in IITA for blended samples. In this case, you have a very good prediction of the dry matter content. We also try to establish this correlation on cross-section of yam. In this case, the prediction is okay, but not so precise than on blended samples. You can see, for example, that the RM SOP is a higher 2 point than the SEP obtained with a blended sample, which is a 1.4. And this is due to the heterogeneity in the yam tuber. You can see here hyperspectral images obtained on a cross-section of tubers, proximal, central, and distal part of tubers. And you can see with color code the dry matter content. The blue value has the lower content, as the red value has the higher values. And you can see, for example, for the proximal cross-section, that the dry matter content ranges from 30% in the center of the tuber up to more than 50% at the external part of the tubers. And in the distal part of the tubers also, you can see that the dry matter section is dry matter content is much lower, and there is almost no variation in the inner part of the tuber, in the distal part. Okay, so it is very important in this case to analyze all the parts of the tubers, and also to take into account that there is a large variation within tubers and within the different part of the tubers to establish a good value of the dry matter content in the tuber. So let's have a look now on the pectin content. Pectin can have an influence on the texture of the yam, and this will be illustrated in the presentation of Aliénor this afternoon. So if you want to determine the pectin content, you have to first dry your samples, grind them very finely, and after that we developed a procedure of the extraction of pectin and colorimetric determination. The extraction is quite simple at moderate temperature at pH 10, and colorimetric determination with a with pre-hydrolysis acid hydrolysis. We wrote the SOP, and there is several critical points which you have to be very aware of this critical point to obtain very good results of pectin results. So if you follow the procedure, you can have a quite good result, and we show, for example, for 4 cultivars, you can see the results, 3 replication with on these 4 cultivars, and you can see that the coefficient of variation between measurement is less than 10%, and you obtain a quite good discrimination between samples. Here you can see here, and the pectin content can range between 500 to 3,000 milligram per gram, depending on the cultivar. And also, we can see that there is a large variation also between tubers of the same cultivar. So, as for water content, you have to determine the pectin content on several tubers for the same cultivar to obtain a good results, good mean value of this cultivar. So as for water content, we obtain a quite good discrimination between cultivars, but also between tubers. So you have to take into account this large variation in composition of tubers in the case of yam. This will be the case for all the component analysis you will develop in the case in the yam. So we try to establish a relationship with quality, and you can see there is a quite good correlation between pectin content and penetrometry force after boiling of yam. But there is however some outliers, and you can see here 2 values obtained with the same cultivar, 2 tubers of the same cultivar, and these tubers have quite high pectin content, but quite moderate penetrometry force. This can be linked in this case to other component. In this case, you can see these tubers on red are quite correctly correlated with penetrometry force when you take into account the amylose content. So we can establish in this case too a correlation between pectin content and amylose and the texture of steamed yam. Okay, so this was 2 examples on how to establish how to define reliable and meaningful biophysical attributes. So I just want to summarize this again. So you have a first step to identify biophysical candidates, then to define the procedure and to write the SOP and to really take into account the critical point of the SOP. Then test the reliability and discrimination between cultivar, and we saw with these 2 examples on water content and pectin that you have to take into account the large variation between tubers and also the large variation between the position within the tubers. So you have to perform several analyses for 1 tuber, and several tubers has to be analyzed to have a proper mean values for every component. Then you can establish relationship between this component and quality attributes. We saw that it can work on with water content, pectin content, amylose content, for example, in the case of texture. And you can, after that, build a database for near calibration. And this approach will be illustrated by several examples by the partner after this presentation this afternoon. Thank you for your attention.